Great. Okay. Well, happy Friday to everybody. It's second week Friday. We're 20% through the quarter, and very. Let me this going lecture 2. Okay. Okay, and so far we've been discussing generating random values from different distributions. If we assume that the computer can generate random uniform, and based on that, can we get random other things? Okay, and so we looked at a bunch of methods. So far, we've covered methods to generate values from different distributions. Generate, I should say, random values. Okay, and so methods we've covered so far have been inverse CDF, rejection sampling, and then we've covered transformation, composition, and convolution methods, right? But so far, all of these have been univariate methods, okay? So we get, values from one for one random variable. Okay, so today we will look at a way to get kind of bivariate distributions, or from higher values from random distributions that are not independent. Okay, so now generating values from a bivariate distribution, and specifically we will look at the bivariate normal. And so right now we're going to say that so far we're able, either using the Box-Mueller transform or some other transform method, we are able to get values from a normal distribution, right? So via Box-Mueller or some other we can get Z to come from a normal distribution, and we can we can modify that to give us values from with a different mean and different standard deviation as well, right? We just multiply by the standard deviation, add the mean to it, things like that. What if we want, okay, values from the bivariate normal? Okay, so bivariate normal will be n sub 2, the sub 2 kind of indicating it's two-dimensional. And instead it will have a mean vector mu and a variance covariance matrix sigma. Okay. So the mean vector is equal to mu1, mu2, and then kind of your variance covariance matrix sigma is sigma 1 squared, sigma 2 squared in the diagonals, and then the covariance in the off diagonals, where sigma 1, 2 will be the covariance between kind of x1 and x2. So if I say this will be the expected value of x minus mu1, x1 minus mu1 times x2 minus mu2. So that's just the definition of the covariance of these. How this will work, okay? All right, so can we do this? Well, so far, what we can do, we can generate two-dimensional z's, okay, where we will say z is equal to z1, z2, where z1 comes from normal 0, 1. Z2 comes from normal 0, 1. Okay, and if we sample Z1 coming from the normal standard normal and Z2 coming from the standard normal, then that would make Z1 independent of Z2, right? And so Z, if we stick Z1 and Z2 together, would come from a bivariate normal. What would the mean be? 0. It would be the 0 vector. And what would the variance covariance be? It would be the identity matrix, okay? So the 0 vector would be 0, 0, and then the identity would be, okay, because Z1's coming from standard normal, so it's going to have a variance of 1, and Z2 comes from standard normal, so it has a variance of 1, but they're drawn independently, so there's going to be no covariance between these two. Okay, so this is kind of our starting point, and we want to somehow go from Z to an X, where X does have some kind of covariance here. Okay, if we were to graph this, draw this. Okay, so if I got Z1 and Z2, I would just kind of have these concentric circles, right? It's kind of hard. Something like this, okay? And you'd have points scattered about, right? So that's what we have, okay? So we want to go from Z to X, okay? Where X, so Z comes from normal this, and we want X to come from normal this. Okay, that's what we want. Okay. let's think back to the univariate case. Okay, so let's say I'll use different letters here. So let's say I'll use the same letters. Okay, so for the univariate case, let's say z comes from normal 0, 1, and we want x to come from normal mean mu sigma. Okay, so this is univariate. How did we go from z to x? What do? We say x is equal to, and what did we do? So if I generate a single random value from the standard normal, and I want I want to transform these to have still a normal distribution, but centered at mu and has standard deviation sigma, how do I go about doing this? Yeah, it would be mu plus sigma times z, right? Okay. Or just kind of, if we wanted sigma squared or something, we would do, yeah, mu plus sigma times z, okay? And so this will kind of give us like a hint of how we should go about doing something like this, okay? We're going to take our z's and we want to multiply it by something and add something to it so that the z's will, the resulting value, the x, will have this thing, okay? So we propose to let x equal, and we're going to take some vector b and add it to some matrix A times z. Okay? So again, z comes from our bivariate standard normal, and we want x to come from this thing. Okay. So we're going to say x comes from here, all right? So then what should b equal and what should a equal so that x will have these properties, right? Okay. Well, we'll start, but let's find the expected value of this x as we've defined it, okay? So we'll call this mu sub x will be the expected value of this thing. So this will be the expected value of b plus az, okay? B is a vector, is a constant. So we can just we can pull that one directly out, right? So we'll have b plus the expected value of a times z, okay? Z is a random variable, so that makes sense that we got to find the expectation of that. A is a matrix, but also a constant, okay? Matrix of constants. So here we're going to get b plus a times e times z, okay? And again, z comes from normal 0, I. So what's the expected value of z? It's going to be the 0 vector. So what we get is that the mean of our expected value of our x variable mu sub x is equal to b. Okay. So if we want x to have mean mu, to have a mean vector mu, then we will set b equal to that mean vector. I should throw vector symbols over there. And that's what we have. Okay, does that make sense? All right, what about A? All right, so what should, or not even just A, but what should we have so that our covariance will have the desired covariance, right? So the all right. What is what's going to be the covariance of this thing? Okay, well, again, b is a constant that is added to az. Okay, so we can throw it away, right? Because that has no effect on the covariance. So covariance of this thing is just going to be covariance of az. Okay. So how do you pull out a when you're multiplying something by a constant? So the random variable is z, and you multiply it by a constant. What do you get? Yeah. So if it's just a single term, it would be kind of a squared times the covariance or variance of z. But because we're dealing with a matrix form, we pull out the a in the front, and then we get that, and then we have to throw the a in the back for the transpose. Okay, and then once again, z comes from normal with mean 0 and variance covariance I. So the covariance of z is I, and here we get AA transpose. Okay, so this is going to be, this is the covariance matrix, variance covariance matrix of our x variable. All right, so if we want x to have some covariance sigma, then we must find find A so that AA transpose is equal to sigma here. Okay. All right, did everyone get a chance to respond to our poll here? Okay, I'm going to go ahead and close that down. Okay, so this is what we need. So we need to find A so that AA transpose equals our desired sigma. Okay, and does this look familiar? AA transpose equals sigma. Finding an A there. Linear algebra. Do you remember? So it's a, what's it called? Is that what, it might be? Yeah. Yes. Huh? It's a certain decomposition, right? Okay, so we've got for any symmetric, positive, definite, Don't you just love these terms? Positive definite matrix sigma, we can find a lower triangular matrix A so that AA transpose equals sigma, and this we call the Cholesky decomposition. Okay, so we will let A equal, and we will have term 1, 1, term 2, 1, term 2, 2, and it being lower triangular, it will be like this. Okay, and we want AA transpose to equal sigma, and we will say sigma is going to be equal to sigma 1, 1 squared, sigma 1, 2, sigma 1, 2, sigma 2, sorry, not 1, 1 squared, sigma 1 squared, and sigma 2 squared. Okay, so this is what we want. I'm going to go ahead and just go to the next slide. I don't think I'll be able to fit it in here. Okay, so A transpose would look like this. It would be term 1, 1, 0, term 2, 1, term 2, 2, times the transpose, term 1, 1, and this transpose term 2, 1, 0, term 2, 2. And we want this to equal sigma. So we're going to set this equal to sigma 1 squared, sigma 1, 2, sigma 1, 2, sigma 2 squared. Okay, so then we just do some matrix multiplication. And so here I would get term 1, 1 squared. And then over here, I would get term 1, 1 times term 2, 1. And then you add a 0. And over here, you get term 2, 1 times term 1, 1. And then over here, I have term 2, 1 squared plus term 2, 2 squared. And this is equal to sigma 1 squared, sigma 1, 2, sigma 1, 2, sigma 2 squared. Okay? All right. So basically, we just set all these things equal to each other. So I got term 1, 1 squared is equal to sigma 1 squared. And that gives me that term 1 is equal to root sigma 1 squared, which is sigma 1. So term 1 equals sigma 1. Okay? And then if I use that in the next thing, then I got term 1, 1 times term 2, 1 is equal to sigma 1, 2. So we know that term 1, 1 is equal to sigma 1. So this becomes sigma 1 times term 2, 1 is equal to sigma 1, 2. And so this becomes this. And then lastly, I got this. T21 squared plus T22 squared is equal to sigma 2 squared. And we learned T21 is this. So I got sigma 1, 2 over sigma 1 squared plus T22 squared is equal to sigma 2 squared. So solving for that, I get T22 is equal to the square root of sigma 2 squared minus I think my batteries just died. Okay. Am I back online? Yeah. Where am I? Okay, and then sigma 1, 2 over sigma 1 squared, all inside the square root there. Okay, and great. So we just put all of this together, and we get our A matrix. All right, is this all right? Nobody? It's just algebra, right? Okay, so we'll say A is then equal to, I forgot. Yeah, let me just write this out. Okay, so I got sigma 1, sigma, the covariance, sigma 1, 2 over sigma 1, 0, and then that term here, sigma 2 squared minus. Okay, so we have A is equal to that, and then we said B, our B vector is going to be equal to our desired mu vector, which will just be mu1 and mu2. And then we'll let x is equal to b plus a times z, okay? Where and z comes from normal with mean 0 and identity matrix, okay? So, and this is equivalent to just having z1 and z2, where z1 comes from normal 0, 1, which we can now generate, and z2 comes from normal 0, 1. Okay. All right, is that okay? All right, so then, so if we do this, we should now be able to kind of generate our values from accordingly with R. I'll post probably post a new homework assignment soon, okay? Like today, and then and I'll probably do be new next week, okay? Covering newer stuff, right? Okay. All right. So how do we want to do this? Okay. So we assume that we now have an R norm function. Okay. So, you know, either we did, you know, Box-Mueller or something. Now we have an R norm function, and so we can generate values here. Okay. And so here I can do, I can generate z. So I'll do z1. Let's do n is equal to 500, okay? And then so I'll do z1 will be R norm 500, and z2 will be R norm 500, okay? I'll just use equals here, okay? So I've got that, and then we will define capital Z as, I'm going to just bind Z1 and Z2. Okay. And then so actually to plot this, I need to transpose Z, okay? All right, and let's just clean up our plot. I'm going to do aspect ratio 1, which I always like to do, and then PCH. Let's use 19, and then I'm going to make our plot points a little bit smaller, so I'll use CX equals 0.5, okay? So that's Bivariate Normal. Here, let's set a seed. Just, okay. Okay, so there is our random bivariate normal, and what we desire is to produce, so this is random normal, and if we ask, what's the covariance of Z, I gotta transpose this, because R is expecting columns, the things to be in columns. So here we'll get something close to the identity, 1 and negative 0.04 and 1.11, okay? So close to the identity, of course not exactly, because it's an empirical thing. Okay, now let's say we desire X to come from norm, and we'll say the mean, I don't know, we can set it to be 3, 4, and then what do we want? We want covariance matrix 1, 0.7, 0.71. Let's do that. Okay, so what I'll do here is I'll say mu is equal to 3, 4, and then I will do sigma is equal, and I can just r-bind 1, 0.7, 0.7, 1. Right, whoops, I forgot the C. It's very important. Okay. And indeed, sigma looks like how we want. Okay. And so now I need to decompose sigma. I can do this, right? I can say T11 is equal to square root of 1, and then T21 is equal to what is it? The sigma 1, 2 divided by T11, and then T22 is equal to the square root of, what is it? It's going to be sigma 22 quantity squared minus T21 quantity squared. Okay, and I should call this sigma 1, 1. So this is one way to do it, and then we'll say A is equal to the matrix of, and we would paste all of these things together, T11, T21, 0, T22, and rho equals 2, right? So this should work out. And let's take a look at what A looks like. Okay, and then if I do A times transpose A, indeed I get what I desire. Okay, we can also shortcut this by doing, there's a, not Cholesky A, Cholesky Sigma. You can, there's a function called col for Cholesky Decomposition. It gives you the upper triangular matrix instead of the lower triangular matrix, so we just transpose that. And then, so if we ask, how does this compare to A, we see it's exactly the same. Okay, so I could call this little a, and we'll see that A times little a transpose A also gives, also gives me back the other thing. So what we did, we did the algebra and we figured it out this way, and we got our terms. But we can also just cheat and use R's built-in Cholesky decomposition function. Okay. Yeah, for a 2x2, it's not that bad. For bigger matrices, it gets a little messier, but it's still easy. Okay. All right. So now we are going to say we're going to generate our X by taking our matrix mu and adding it to A times our matrix Z. Okay, and then just because of the way we have X it's in rows. You know, when we wrote this out, we said, you know, z is equal to, you know, z1 and z2, and thus if we have 500 values, our big matrix Z ends up being kind of like z1, the first value, z2, the first value, and then z1, z2, the second values, dot, 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 all the way up to z1, the nth value, and z2, the nth value. Okay, and R expects things in kind of column form, where we want z1 to z1n, and z2, and z2n. Wants it this way, so that's why I'm transposing them. All right, so I can plot x. What will x look like now that I've transformed them accordingly? No, not z. X. Okay, so that's what we get. So we have so z, and then now that we said there's covariance between these two things, it looks like this, which is desirable. We can ask what is the mean of x. So I got to transpose these again. Oh, not mean, column means. Okay, and that is close to what we desired. And then we can ask also for the variance of x, or the covariance. It's going to give us the same thing. Okay, and we do get terms that are close, not exactly, but close to what we requested, right? If I crank up our values to something higher, okay, so here we get something very close to what we expected. We can specify things this way. And we'll set our x equal to that. So that looks good. and there we go. Okay, and then you know, now that we've defined our a's kind of this way, you know, we can give it any variance covariance matrix. So we could give it, we can say we want it to be quite much bigger this way. Okay. If I did this now, okay, and so, you know, changing the way it goes. So, you know, in the x1 direction, it's got a total variance of 1. So, you know, most of your values centered at, what did we say our mu vector is? So our mu vector is centered at 3, okay? Here, let me just do AB line h equals 4, and AB line v equals 3. So this is kind of where we're generating our mean values, and we can see that indeed, if I go up two standard deviations, and I go down 2 standard deviations. So that seems, from the vertical perspective, it does seem to capture about 95% of our data, okay? And then if we go horizontally, each standard deviation, because our sigma is 4, each standard deviation is 2, so I need to go up 4. And down 4. Okay. And that, oh, not 3 plus 4. I was like, this doesn't look right. Shoot, I gotta redo this plot now. Darn you. Okay. let's reduce our density a tiny bit, or let's make our plot dots even smaller. Okay, so we have okay, and then what did I say our mu vector is? Is it 4? It's 4. Okay. 4 plus 4 and 4 minus 4. Okay. Okay, and that does seem to kind of box off kind of like the middle 95%, vertically, and the middle 95% horizontally, and things of that nature. Okay, and of course, if we looked only at one variable at a time, so if I did just extracted the first, I'll call this x1. And I ask for a summary of x1. Indeed, we get a mean close to 3, and we can kind of see that that our values follow what we expect. If I plot a histogram of x1, it does look normal. Okay, we can do the same thing for x2. Plot a histogram of x2. So these are indeed, each x and each x2 are indeed normally distributed, and when we plot them together, we can see that they do indeed have the kind of desired covariance, expressing that they're not just independent of one another. Okay. Are there any questions on this? All right. I guess any last-minute questions from the homework?
What's the P thing you're talking about?
The what?
The P that you're talking about?
Oh, okay. So I think a lot of people had questions about the chi-squared test and this warning about the thing being wrong. Yeah. You need to collapse the categories for 5 and 6, and then when you run the chi-squared test itself, you do chi-squared.test. You give it the vector of observed counts, comma, and then you have to say P is equal to the vector of probabilities. If you look up, so whenever something doesn't work, when you're trying to do something and it doesn't work, always just ask for the help on the thing, okay? And you can see that the default arguments are X, and then if you give it a second argument, it's expecting it to be Y, okay? And both of these, there's expecting them to be, kind of these numeric vectors of counts. But what we want is we want to provide it a vector of probabilities, okay? And in that case, if we're going to use that, we have to give it P. So P is going to be the vector of probabilities, so you need to tell chi-squared test, you're going to give it the vector of counts X, and then you're going to give it the vector P of probabilities, okay? So that's what we have. And yeah, that's it. Okay, so we'll see you guys on Monday. I'll probably post up a homework assignment covering these other random number generation methods, and we'll see you guys on Monday. Have a great weekend.
We really are.